So, Noether's theorem part 2. We're just going to run through what the Lagrangian is and explore it as a slightly different way of explaining motion and forces. So the traditional way we've been taught by schools, obviously, is that motion is caused by forces like gravity, or the force produced by our muscles pulling on or throwing something. Motion just describes change. Now, this is because objects are obviously inanimate things. They're not going to move on their own. So the path of least resistance, i.e. the lowest energy route, will be to follow the force being applied to them. So at the end of the day, we don't actually need the concept of forces to be able to describe motion. All we need is to know if its position and velocity through time is changing. Let's just quickly go through a worked example. I'll leave you to read this and pause here if you want to work through it yourself before we dive in a second. So, acceleration due to gravity is 9.81 meters per second. And we can use Newton's second law to find the downwards force. F equals ma. So here's our calculation. F equals 294 newtons. The person supplied 200 newtons of force, but the downwards force acting on the ball is 294 newtons. So the ball would move downwards with a force of 94 newtons, as this is the path of least resistance. To give it a go, have a little look at section B of the worksheet. Right, back to the Lagrangian. You're used to considering the motion of objects, as we discussed in the previous session, generally as being caused by various different forces. If we know the position and velocity of an object, i.e. the speed and its direction of travel, we can predict exactly how it will move. This is the idea behind trajectories, like we talked about. Now, the question does remain, how can we combine position and velocity to give a useful theory here? We will consider the previous example of a ball being thrown through the air. The kinetic energy, usually called T, is given by T equals half mv squared, where v is the velocity. It contains information about the speed of the ball and the direction it's moving. The potential energy, usually called V, is given by V equals mgh, where h is the height above the ground, the position of the ball. Therefore, you can see that the energy of the ball is related to both position and velocity. It means that if we know the kinetic and potential energies at a specific point in time, we can work out the entire trajectory. This is what Lagrangian mechanics is, a description of changes in energy. This is done using a quantity called the action. The action describes a specific trajectory that an object will take. So, as we showed here, this means each trajectory in space and time has a different action associated with it. In order to develop this further, let's go a little bit more into the maths behind it. L is a function of kinetic and potential energy, or T and V. It's defined as the difference between these two energies. So, kinetic energy minus potential energy. To define the action in that case, we're going to sum over L over the whole trajectory. The best way to do this will be using an integral. The action in this case is just an integral of the Lagrangian with respect to time. So, as we discussed earlier, objects will follow the path of least resistance. And this can be expressed in the action. Objects will move so that the action is minimized. So, its trajectory in a certain scenario will be easily and intuitively predicted, as it will always be when the action is, as we call it, stationary. This is the principle of stationary action, or principle of least action. Great. So now you should know how to explain some basic laws of motion using the Lagrangian, and realise that forces aren't necessarily the only way to interpret this. Next time we'll get right into Noether's theorem and see what it's all about.